All right, let's talk about ordinary points today. All right, so start off with a definition. It says the linear homogeneous differential equation yn and then a plus a1, not all of this guy, right, equals zero. So homogeneous, so it's equal to zero, is said to have an ordinary point at x naught if each coefficient function ai is analytic at x naught. And then any point that's not an ordinary point for the differential equation is a singular point. So we talked a little bit, we didn't use it yesterday, but in section 2, we talked about the definition of analytic. And for polynomial functions, it was basically if your denominator can't equal 0. As long as if you don't have a denominator equal to 0, then you've got an ordinary point. But otherwise, you've got a singular point. So the singular points happen when you're dividing by 0 for those coefficients. So let's do an example. Example 1, it says to find the singular points. And the singular points happen when your coefficients are divided by 0 of y double prime plus e to the x over x times x minus 1 times y prime plus cosine of x over x plus 1 times y equals 0. All right, so you've got singular points where it fails to be analytic, and it fails to be analytic when the denominator is 0. So when x equals 0, when x minus 1 equals 0, and when x plus 1 equals 0. There's where it fails to be analytic. And so the singular points are at x equals 0, at x equals 1, and at x equals negative 1. All other points other than these 3 are called ordinary. All right, not too shabby. We got a theorem that I would rather not have to write. So this theorem says, given the linear homogeneous differential equation, so same one as that one up there, with your a1 through an all analytic at x naught, with convergent power series at x naught on the interval where x minus x naught is absolute value is less than r, then every solution to the differential equation is analytic at x naught, defined by its power series on the interval absolute value of x minus x naught less than r. All right, so we're going to use that. We're going to find the general power series solution centered at x equals 0 for the given differential equation. All right, so let's do that. We're finding the general power series. Solution centered at x equals, your x naught is 0 here. For, let's start with example 2 is y double prime plus y equals 0. So here you don't have, like, your coefficients are a 1 and a 1. So there's no singular points. And so x equals 0 is definitely an ordinary point, which means that we can find the solution by its power series. Okay, so here's what you're going to do. You're going to use the fact that in general, the general power series from section 1 is starting at 0 to infinity an x to the nth power. That's your general power series. And then the derivative of this, you start with n equals 1 now to infinity, and you would do pop and drop on this, pop the n. You're taking the derivative with respect to x, right? So an you'll leave, but you'll have a an and then times n times x to the n minus 1 power. And then the second derivative would be starting at 2 to infinity of an, and then you have n, and pop and drop this guy times n minus 1, and then now it's times x to the n minus 2. So those are the things that we're going to use. You definitely need to know these guys. This is not the answer. Just make sure you recognize those because we're going to use those on all of them, right? So here's what we do. These are the general power series. We're going to take these guys and we're going to plug them in and substitute them into this original equation. Into the original equation, which is y double prime. Okay, well, that's this guy. Y double prime plus y equals 0 is the equation we're plugging it into. We're going to replace it with their power series. n times n minus 1 to the x times x to the n minus 2, and then plus y is this power series, n equals 0 to infinity a n x to the n, and that's equal to 0. Then what you want to do is, the next thing we're going to do is we're going to shift the indices. We did this the other day too. I've got an x to the n and I've got an x to the n minus 2. I need them, I want them to both be the same exponent on the x. All right, so we're going to shift the index. Well, plural is indices. All right, so what I'm going to do is I'm going to I'll let k be n minus 2, which then means that n will be k plus 2. Okay, and so then that means that I'm replacing this guy. So now instead of n equals 2, I'm going to have k plus 2 equals 2 to infinity, which that means that that's going to be changing to just k equals 0. Instead of a sub n, it'll be a sub k plus 2. Instead of n here, I'm going to have k plus 2. Instead of n minus 1, replacing the n with k plus 2, so you'll have a k plus 2 minus 1, and then an x to the n minus 2 would be a k plus 2 minus 2. Yeah, and the other guy we're just going to keep the same. We don't need to change him. Okay, that's what we got so far. So let's clean this up. That means this is a k equals 0. If k plus 2 equals 2, k subtracting 2 on both sides, your k is 0 to infinity. This is a k plus 2 times k plus 2 times k plus 2 minus 1 is a k plus 1. X to the k plus 2 minus 2 is just a k. Yeah. And then plus this guy. Okay, I'm using k's here, so I'm going to switch these to k's. No big deal. Just switching the letters. No big deal. Okay. Now I've got both of these are x to the k's, so I can factor that out. They're also both starting with k equals 0 to infinity, so I can write them as a single sigma starting at k equals 0 to infinity, and it's a sub k plus 2 times k plus 2 times k plus 1. I'm going to factor out this x to the k, so then I have a plus a sub k. That's my new coefficient there, and then times x to the k equals 0. Yeah, so all I did was they both have the same index. They're both x to the k. So I was able to factor them out. And we got that. All right, so now what you're going to do is equate the coefficients. Yeah, they're on the right hand side, you've just got 0. So what that means is that this guy must end up equaling 0 because we don't have an x to the k on this right hand side. If it had been plus 2x to the k or something like that, okay, then you've got that this would equal 2. But we have it equal to 0. So that means this must equal 0 because we don't have an x to the k term on the right hand side. So we equate coefficients. And that is that a sub k plus 2 times k plus 2 times k plus 1 plus a sub k must equal 0. All right, these are two different terms, and so I'm going to solve for a sub k plus 2 and put it in terms of a sub k. So I'm going to subtract it. Yeah, so you've got an a sub k plus 2 would be a negative a sub k, and then these two guys were multiplied times this, so I'm going to divide by k plus 2 and k plus 1, and this is for k greater than or equal to 0. All right, now we're going to be able to define each of these a sub k's in terms of the a sub k's, right? We're going to be able to rewrite them. Most of the time, not always, but most of the time, the even k's are going to be different than the odd k's when you plug them in. So I'm just going to automatically separate them because you'll find as you go along that they do end up being, that's the difference between them. So when k is even, and then I'll also do hopefully I've left myself enough room when k is odd. You'll see what happens as we're doing it. Okay, so when k is even. So when k equals 0, well, when you plug a 0 into k, you would have a2 is equal to negative a0 over 0 plus 2 times 0 plus 1. So it's over 2. Yeah? Okay. When k is 1, you would have an a sub 3, so I'm plugging ones into the k's, equals a negative a1 over 1 plus 2 would be 3 times, let's do that, 3 times, maybe I should have showed that, 2 times 1, 3 times 2. You're plugging a 1 into each of these k's. Okay. When k is 2, you would have a sub 4 is equal to negative a sub 2 over, plugging in a 2 here would be 4 times 3. Yeah. But then, this is what we're really going to be doing, I know what a2 is. Yeah. a2 is this guy. So that means I'll leave the negative 1 over 4 times 3 here, but then instead of the a2, I would do negative a0 over 2 times 1. Now, when k equals 3, you would have a5 is equal to a negative a3 over, that would be 5 times 4. But we know what a3 is. It's this guy. So that means this is a negative 1 over 5 times 4, and then times negative a1 over 3 times 2. When, how many am I doing? K is 4. When k equals 4, you would have a6 is equal to negative a4 over 4 plus 2 would be 6. 4 plus 1 is 5. But I know what a4 is. It's this guy. So that means it's a negative 1 over 6 times 5 times, let's clean this guy up, yeah? This would be a positive A naught over 4 times 3 times 2 times 1. Hoping you're seeing the pattern at this point. When k is 5, you would have a 5 plus 2. That's a7 is equal to negative a5 over 5 plus 2 is 7. 5 plus 1 is 6. But then I know what a5 is. It was this guy, which makes it a, what is that? So this is a negative 1 over 7 times 6, and then times this guy. Negative and a negative is positive, so it's an a1 over 5 times 4 times 3 times 2. Now, hopefully you see the pattern. Do it in a different color. This guy is negative a naught over 2 factorial. This is a naught over 4 factorial. This one is a negative a naught over 6 factorial. You see the pattern? 6, 5, 4, 3, 2, 1. Okay. This one is a negative a1 over 3 factorial. I know it's missing a 1, but times 1 is still the same thing. This guy would be a1 over a positive a1 over 5 factorial. And this one would be a negative a1 over 7 factorial. All right, so do you see the pattern? Hopefully you do. Do you notice all of these guys are even? So when it's an even indexed there, a 2k, right? So k equals 1, and then k equals 2, and k equals 3. Then you would have, they're alternating in sign, negative 1 to the kth power over the even factorials, and then times a naught. That's the pattern on that. Over here, the odd indexed guys are, again, alternating in sign, and over the odd powers times a1. So that's your pattern. Now, so I will show you how to write your answer. Also, okay, I'm going to show you the general solution, right? But then I'm also going to, most of the time, like this was a pretty straightforward pattern. Now, hopefully you thought so. Well, okay. So what does that mean? This guy is, the power series would be a naught x to the 0 plus a1 x1 plus a2 x squared plus a3 x cubed plus a4 x to the 4th plus, hopefully you see that, right? But then we know all of these guys. So a naught is at times x to the 0 is just a naught. a1 times x. Okay. But here's where things change. A2, I know in terms of a naught. This is a minus 1/2 a naught x squared. Now, a3 was negative a1 over 3 factorial, which is a minus 1 over 6 a1 x cubed. You know? And then over here, we have a plus 1 over, I'll just leave it as 4 factorial. 4 factorial, a naught x to the 4th plus 1 over 5 factorial, a1 x to the 5th. Now, do you see all that? So what we can do is group these guys together. So what happens is, notice I can group all the a naughts and the a1s together. And so your general solution will be y equals, I'm going to factor out the a naught from each of these guys, and I would end up having a 1 minus 1 half x squared plus 1 over 4 factorial x to the fourth minus, and then I factor out a 1, and I would be left with an x, and then a minus 1 6x cubed, and then a plus 1 over 5 factorial x to the fifth, get minus next time, right? Like that. So this is going to be good enough, right, is on how you give your answer, unless it's an easy pattern, and this one wasn't bad. And so, but in general, if you go to do the homework and you're like, oh my gosh, how did they see that pattern? Just write your answer like this instead. Now, where you got to find each of the values, and then they're either in terms of A0 or A1, and then factor it out. But for this guy, we really can keep going. This is y is equal to A0 times, this should look familiar to you. This is where k is 0 to infinity of -1 to the kth power over 2k factorial x to the 2k. Yeah. And plus A1 times, hopefully this looks familiar to you too, because that's a 3 factorial and a 5 factorial. So it's k goes to 0 to infinity of -1 to the kth power x to the 2k plus 1 over 2k plus 1 factorial. Yeah, I guess I should have stuck that out front here just to stick with a pattern, but whatever. That's your general solution. Yeah, so if you can find the pattern, great. And in this case, hopefully you recognize that, right? What is this guy? Well, that's cosine. What is this one? Sine. Yeah. And so as a side note, when you solved y prime from, so using previous methods, today's method is we're using series, right? We're using the power series and stuff. But when you went to solve this in previous chapters, this was d squared plus 1 operating on y is 0, where your r is plus or minus I. So that means a is 0 and b was 1. And your solution was y equals c1 times cosine of 1x. Well, because it was e to the 0 x times cosine of x plus some other constant times e to the 0 times sine of 1x. Those are the same things. The only difference is I'm using C1 and C2 instead of A0 and A1. Yeah? I know, crazy. You're like, why the heck would anyone use that on? Yeah, you're right on this. That's craziness. But on other ones, see that it helps. Okay, so again, this was a pretty easy pattern to see. So totally, I would expect you to generalize this. A lot of the ones in the homework are not easily generalizable. And you'll look at it and you'll go, that was crazy. So then don't, and I'll show you. Hopefully this is one more. Oh, I did. Oof. Okay. All right, so we're on example 3. So same directions, we're going to be using, find the general power series solution for this. All right. Do you see there are no singular points? No singular points because there aren't any dividing by 0 or whatever. And so they were wanting us to find the power series centered at 0. And so x equals 0 is an ordinary point. All right, so, and then again, I'll write it again because it's worth writing until you have it memorized, right? y I'm going to replace with a n x to the n. Y prime I'm going to replace with, remember your index starts at 1 now, a n times x to the n minus 1. And then y double prime I will replace with, my index now starts with a 2, a n times n minus 1, and then x to the n minus 2. So those are my replacements. You place it in the original equation. So I'm starting with this guy. We got n equals 2 to infinity of a n times n minus 1 times x to the n minus 2. Okay, I've got a coefficient this time. I got minus 2x, so it's a minus 2x times this y prime power series, n times x to the n minus 1, and then a minus 4 times y, and I'm placing y with that power series there. A n x to the n, and it's equal to 0. Okay, so I'm going to change indices, but I'm also, before I do that, I'm going to distribute this x into here, multiply it through, because x times x to the n minus 1 means I'll just have an x to the n. If you can do that, that definitely helps, because you've got to change all these indices to match and stuff, and you want to start with, you want these n's, it's your powers on x to be the same. That's what you want to start with, right? So I'm going to, by multiplying that x, I now have x to the power of n. I have x to the power of n. I want this to be an x to the power of n. So I'm going to let k equal n minus 2 here, which means k plus 2 is going to be what is equal to n. So this gets replaced with k, okay, so it's technically a k plus 2 equals 2, but that makes it a k equals 0 to infinity of a sub k plus 2 times k plus 2 times k plus 2 minus 1, so that's a k plus 1, and an x to the kth power now. And then I've got a minus 2 times, I'm going to go ahead and just switch all of these. Instead of n's, I'm going to replace them with k's. So this is now a k goes from 1 to infinity of a sub k times x to the k. And then a minus 4, same thing here. I'm just replacing the n with a k. A sub k x to the k. Now, all right. Now, what you need to have happen now is you need x to the k's. Those are all fabulous. You need to all be starting with the same index. 0, 1, 0. So you can shift these guys and stuff. There's more than one way to do it. The way I like to do it is I like to just expand it out until they all match, right, to the larger starting index. Yeah. So if I plug in a 0 into here, into my k's on this guy, then I would, once you plug in a 0, the next thing you would be doing is plugging in a 1. So I'm going to plug in the 0, and then I'll still have this series notation, but now I'll be starting with a 1 here. This one already has a 1, and then this one has a 0, so I'm going to do the same thing here. I'm going to start by plugging in a 0, and then the next part of the series would be having a 1 as the index. So plugging in a 0 here would give me a2 times 2 times 1 times x to the 0. And then now the next thing I would do would be plugging in a 1. But instead of doing that, I'm just going to write, now the series starts with 1. And I've still got the rest of the same thing. Everything else is the same. Does that make sense? I hope so. This whole thing is equivalent to this guy. Now, all I did was I plugged in the 0, and then the series still continues, but now with an index of 1. Because that's what you want. To be able to like factor out these guys, you want your indices to be the same. Okay, so then this is already a 1, so I'll have a minus 2 times k equals 1 to infinity of a sub k times x to the k. And then I'm going to do the same thing here, where I'm going to plug in a 0 here. So this is a minus 4 times a0 x to the 0 minus 4. Now I'm starting with k equals 1. Okay, and then the whole thing is equal to 0. Sorry, I ran out of room. Equals 0. Okay. Yeah. Okay. So I'm going to group up. Keep in mind, this is equals 0, right? Equals 0 on the right-hand side here. So I need to equate coefficients. Yeah. So I have these two guys, right? So I've got a, what is that? A 2a2 is what this one is. And over here, a minus 4a naught. No. And then I have a plus sigma, and I'm gonna pull them all together, right? They're all starting with the k equals 1. They all have an x to the k. So I can group them all together. This is a k plus 2. It's ak plus 2 times k plus 2 times k plus 1 times x to the k. So I'm going to factor that out. And then a minus 2ak times k. I guess I should have stuck that k in front there. Oh well. Times x to the k, but I'm pulling that guy out. And then a minus 4ak times x to the k. X to the k, and then it's equal to 0. Yeah. Okay. So now you've got equal 0. So I'm going to equate coefficients. That means that this guy must equal 0, and this guy must also equal 0, since there's no x to the k over here and constant 0. All right, so we've got that 2a2 minus 4a naught is 0. So solving for a2, I would add 4a naught over and then divide by 2. So a2 is equal to 2 times a naught. Setting this guy equal to 0. Well, we should have cleaned it up a little bit. Both of these are ak's. So I've got a ak plus 2 times a k plus 2 times a k plus 1. And then this is a, how about a minus a sub k times a 2k plus 4. And that must equal 0. Hopefully that makes sense. Yeah. Solving for a k plus 2, I would add that guy over. So I would add it over, and I would have a sub k times 2k plus 4, and then divided by a k plus 2 and a k plus 1. But I see a 2 in common there. So that means this is an a sub k, and then times a 2 times k plus 2. So the k plus 2's will cancel. Yeah. And this is for, so that means a sub k plus 2 is equal to 2ak over k plus 1. And this is for when k is greater than or equal to 1, because we changed our indices to start with 1. Okay. So those are our two patterns. Yes. And you can see, even if you plugged in when k is 0, it fits this pattern. A2 is equal to 2a naught over 1, which gives you this guy too. So, all right, so we're going to split this out into the evens and the odds. Now, when k is even, so when k is 0, right? You would have A2 is equal to 2A naught. Plug in the 0, it totally works. When K is odd, when K equals 1, I would have A3 is equal to 2A1 over 2. Oh, well, that's just A1. Now, when K is 2, you would have A4 is equal to 2A2 over 3. But then I know what A2 is. It's 2A naught. So that means this is a 2/3 times 2A naught. Well, am I going to try and do the pattern here? All right, I'm going to try and show you the pattern here. So this is a 2 times 2 over 3A naught. All right, when K is 3, you would have A5 is equal to 2A3 over 4. So that's just a 1/2 A3. But then A3 is A1, and so 1/2 A1. When K is 4, we would have A6 is equal to 2A4 over 5. But we know what A4 is. So this is a 2/5 times 2 times 2 times 3 A naught. No. All right, when K is 5, you would have A7 is equal to 2A5 over 6. So that's a 1/3 times A5, but A5 was 1/2 A1. Is that good enough? I see the pattern here, definitely. We could do one more. Well, let's do it. When K equals 6, you would have A8 is equal to 2A6 over 7. So that would be a 2 over 7 times A6, but we found A6 was a 2 times 2 times 2 over 5 times 3, and then A naught. And then when K is 7, you would have A9 is equal to 2A7 over 8. So that's a 1/4 times, and A7 was 1/3 times 1/2 times A1. Okay, so do you see the pattern? It's not horrible. And notice the evens definitely have a different pattern than the odds. So here, your pattern is for the evens, it is a 2 to the what? Well, when 2, 2, well, this is when it doesn't match up, right? So when it's even, now your K is 1. And so when your K is a 1, then you've got 2 to the power of 1. When K is 2, you would have a 2 times 2 over 3. So it ends up being a 2 to the kth power. I know that's confusing. Over, notice the bottoms, the denominators are, it's a 1. And this one is a 1 times 3. And a 1 times 3 times 5. And a 1 times 3 times 5 times 7. So it's all the odd numbers. So it's a 1 times a 3 times a 5 times all the way until 2K minus 1, and then times A naught. Over here, the odds is a 1 over 2, a 1 over 6, or how about a 1 over 2 times 1, a 1 over 3 times 2 times 1, a 1 over 4 times 3 times 2 times 1. So it's a 1 over K factorial times A1. Yeah? All right, so your general power series is y equals A naught plus A1 times x to the power of 1 plus A2 x squared plus A3 x cubed plus A4 x to the 4th, blah, 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 right? So that means that you're going to just go and replace these. So I'll show you how do you write it when the pattern is not obvious. You're going to go y equals a naught plus a1x plus a2 was 2a naught, a3 was a1, a4 was 4/3 a naught, x to the fourth, a5 was 1/2 a1, and you would keep on going, obviously showing more. You would want to factor out the a naught and the a1. So a naught times 1 plus 2x squared plus 4/3 x to the fourth plus dot dot dot. And then a1 has x cubed 1/2 x to the fifth. Yeah. And I really, if you're not gonna show me the pattern, you really should be including more. And I found them. I just didn't put them in there because I ran out of room. But so this is if you cannot find the pattern, this is how you end up writing your answer, separating out the a naughts and the a1s. In this case, there really was a pattern, and so it ended up being. Do I even want to do it? I'll write it just so that way when you see the solutions in the solution manual, you're not going, what the heck? So for these y evens, right? For the even ones, that was where you had all these a naughts and stuff, right? And so for the even guys, it was actually a naught plus this series of the 2 to the power of k times a naught over 1 times 3 times 5 times to the 2k minus 1 times x to the 2k, where k is starting with 1 to infinity. Yeah. And then your odds were from k equals 0 to infinity of a1 over k factorial x to the 2k plus 1. And so you write your answer. If you can find the pattern, you would write your answer as y equals a naught times 1 plus this sigma from k equals 1 to infinity of, I factored out this a naught here, so 2 to the power of k over 1 times 3 times 5 times 2k minus 1 times x to the 2k. Yeah, that was times the a naught, and then plus a1 times the sigma k equals 0 to infinity of, I factored out the a1, so now it's a 1 over k factorial x to the 2k plus 1. Yeah, so this is how the solution manual will show the answer. I'm fine with this when, like, this pattern wasn't horrible, but it's starting to get there, right? It's starting to be like, oof, gosh, really? So I'm fine with this. Okay, let's do one more. I know this is a long video, but I'd rather give you more examples. So same directions, yeah. We're going to find the general power series centered at x equals 0 for y double prime minus x squared y prime minus 2xy. Okay. So I didn't give you anywhere where there was a leading coefficient. If there is a leading coefficient, you need to divide through and make sure that it's still analytic at x equals 0. But then you still go back and substitute it into this original equation. So, all right, I'm going to replace these with the power series. Y prime. I'm not going to write it again. Hopefully, look back at it, right? We're going to go from n equals 2 to infinity of a sub n times n minus 1 times x to the n minus 2. That's y double prime. Then you have a minus x squared times the power series for y prime, which is n equals 1 to infinity of a sub n times x to the n minus 1. And then minus 2x times the power series for y, which goes from 0 to infinity of a sub n x to the n, and that's equal to 0. Any x's in front, distribute them in. Now, distribute, so there isn't anything here, but this x squared, let's multiply it times the x to the n minus 1. Same base, keep the base, so this ends up becoming a x to the n plus 1. Yeah, and I'm going to take this, I'm going to do the 2, no, I'm just going to do the x and multiply that times the x to the n. Okay, so first guy stays the same. Going from 2 to infinity, a n times n minus 1, x to the n minus 2, minus sigma 1 to infinity of a sub n times x to the squared times n minus 1, be n minus 1 plus 2, so it becomes an n plus 1, minus 2 times, going from n equals 0 to infinity, x times x to the n comes an x to the n plus 1. Okay, so I want all of my indices to be the same. I've got an n plus 1, and I've got an n plus 1. So, well, and yeah. So let's let k be n plus 1. So then k minus 1 will equal n. Yeah. And then over here, I'm going to let k be n minus 2. So then k plus 2 will equal n. Yeah. Okay. So that's going to get all of my x's to be x to the powers of k. That way they all match. So when I go and I replace this, n is k plus 2. So k plus 2 equals 2 means I'm going to be starting with k equals 0 to infinity. A sub n is k plus 2. K plus 2. K plus 2 minus 1 becomes a k plus 1. And then x to the kth power. And then a minus. I'm letting n be k minus 1, which means this guy, when you do k minus 1 equals 1, means this guy's going to be starting with a k equals 2 to infinity of a sub k minus 1 times k minus 1 times x to the kth power now. And then a minus 2 times, it's going to be an x to the k and an a sub k minus 1, x to the k. N is now at k minus 1. K minus 1 equals 0 means this guy will be at k equals 1 to infinity. All right, so what you want to do now is, there's more than one way to do it. This is the way I like to do it, is I'm just going to start expanding out the series. I need all of these indices to match. And you got to get them up to the largest one. 2 is the biggest one out of the indices. So I'm going to start by plugging in a 0 into k here, and then I'm plugging in a 1 into k there, and then what will be left is starting with an index of 2. So starting with k equals 0, that would be an a2 times 2 times 1 times x to the 0, plus, now plug on a 1, and you would have a3 times 3 times 2 times x to the power of 1. And then I have the sigma notation, but starting with k equals 2 now. else stays the same. Okay, and then I've already got a k equals 2 starting there, so I'll just write that one. Infinity a k minus 1. Of course, I'm going to run out of room. Okay. Then I'm going to, this is starting with a 1. I needed to start with a 2, so I'm going to plug in a 1 here. So that means it would be it's a minus 2 times a naught x to the power of 1. Yeah. And then a minus 2, but now my index is starting with 2 here because I plugged in the 1. A k minus 1, x to the k, and then it's equals 0. All right, so we need to equate coefficients. Yeah. And so do you see that I've got an x to the 0? So that's just a constant there. This is an x to the power of 1. So is that one. All right, so let's do that. This is a 2a2. This is if I factor out the x, this would be a plus 6a3 minus 2 a naught times x to the power of 1. Yeah. All right, so I took care of that and that and that, and then I still have these 3, but they're all starting with an index of k equals 2. So from k equals 2 to infinity, I'm going to factor it all out, and they're all to x to the k. So it would be an a k plus 2 times k plus 2 times k plus 1, and minus a k minus 1 times k minus 1. And I already got that guy. And then a minus 2 a k minus 1. All of that was times x to the k. And then this whole equation is equal to 0. Another room there. Yeah. All right. Now I can equate coefficients. Yes? It's equal 0, which means that this guy must equal 0. The coefficient on x to the power of 1 must equal 0. And coefficient on x to the k must equal 0. All right, so let's do this. We got 2a2 equals 0. Oh, well, a2 is equal to 0. We got 6a3 minus 2a naught must equal 0. So that means a3 would be add the 2 divided by 6. So a 1/3 a naught. And then this guy. Okay, well, those two guys are both an a sub k minus 1. So really we've got an a k plus 2 times k plus 2 times k plus 1. And then a minus, and if I factor out the a k minus 1, I would have a times k minus 1, but then a plus 2, because I already factored out the minus there. Plus 2 is equal 0. Is that right? All right, so that means that's a k plus 1. So that means a sub k plus 2 would be, adding that over, we would have a k plus 1 times a sub k minus 1 all over k plus 2 times a k plus 1. K plus 1's cancel, and so your k plus 2th term will be a sub k minus 1 over k plus 2, and this is for when k is greater than or equal to, our index started at 2, so 2. Yeah? Okay, so let's write them out. Those are our patterns. Split up the k equals 0. So here's one where when k equals 0, it doesn't make any sense because you would have a negative 1. But when so when k equals 0, you would have a2, but we figured out a2 is 0. If you plug it in, you'll have an a sub negative 1, and that doesn't make sense. There's not a negative 1 term. So a2 is 0. For the odds, when k equals 1, you'll have a3, and you'll see it matches this, that it's equal to 1/3 a naught. All right, when k equals 2, you'll get an a4 is equal to a1 over 4. And when k is 3, you'll get a5 is equal to a2 over 5. But a2 was 0. Yeah, so that's a 0. All right, when k is 4, you'll have a6 is equal to a3 over 6. But we know what a3 is. A3 was 1/3 a naught, so that's a 1/6 times 1/3 a naught. When k equals 5, you would have a7 is equal to an a sub 4 over 7. But we know what a 4 is. So this is a 1 over 7 times a4 was 1/4 a1. Now, when k equals 6, you'll have an a sub 8 is equal to a5 over 8. But a5 was 0. So 1/8 times 0 is still 0. When k is 7, you'll have a9 is equal to a sub 6 over 9, which is 1/9 times a6, which was 1 over 6 times 1/3, and then times a naught. Yeah. How many do I need to do? Got 9 and is it enough? 1, 2, 3, 4. 1, 2, 3. Let's do one more because right now I've only got. Let's do one more. When k is 8, you'll have a10. Yeah, would be a sub 7 over 10. And a7, so this is a 1 over 10 times, and a7 was 1 over 7 and a 4, and then times a1. Okay, I think that's going to be enough for us to figure this out. Now, how you put together your answer, remember the general power series is y equals a naught plus a1 times x to the power of 1 plus a2 x squared plus a3 x cubed plus a4 x to the 5th plus a4th. A5 times x to the 5th plus a6 x to the 6th plus yes? All right, so we start plugging these guys in. So this is a naught plus a1 x, and then plus, and then here's where things start changing. We got 0. Plus a3 was 1/3 a naught x cubed. A4 was a 1/4 a1 x to the 4th. A5 was 0. A6 was a 1 over 18 a naught x to the 6th. Yeah, I better keep going. Plus a7 times x to the 7th, so that's a 1 over 28 a1 x to the 7th plus a8 times x to the 8 plus a9, which is a 1 over whatever 9 times 6 times 3 is, a naught x to the 9th plus a10 times x to the 10th. So this is I'll come over here, plus a 1 over 10 times 7 times 4, a1 x to the 10, and it keeps on going. Yeah. And so how you'll write your answer, because notice they're all in terms of a naughts and a1s now. You'll write your answer as a naught times what would be a 1. That's an a1. That's a 0, right? Don't a naught. So plus 1/3 x cubed. a1, 0. Here's an a naught plus 1 over 18 x to the 6th. a1, 0. Here's an a naught plus 1 over, I can do this, 162, I think. Hopefully I did that right. X to the 9th, and then that's an a1, so plus dot, 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 plus a1 times, yeah, and I have an x. We're going for a1s, plus 1/4 x to the 4th, 0, a naught, a1 here, so plus a 1 over 28 x to the 7th, 0, a's not, a1, plus, so 1 over 280 x to the 10th, and then plus dot, dot, dot. That's how you're going to write your answers. Yeah. There is a pattern. That one too, is there? Yep. There is a pattern. This is just for you brainiacs that really want to see the pattern. The pattern was this. And again, you don't need to, this one is one that I consider crazy, and you don't need to know it. You can just write your answer like that. But what is the pattern? It's a 1 over 3n times n factorial x to the 3n plus a1 times, you ready for this one? It's a 1 over 3n plus 1 times 3n minus 2 all the way down to times 1 times x to the 3n plus 1. But you don't need to generalize it to that. Perfectly fine with you giving me this answer right there. All right. Ordinary points. Nice. Writing your solution to a differential equation